Okay, so hello everyone, let's get started. This is our Distinguished Lecture Series seminar. It's actually the last one in this term series today. The DLS seminars are the main high-profile scientific event of our institute, the Max Planck Institute for the Science of Light. And it's a means to engage the most important and influential colleagues in any area of the science of light. So this is why we have the pleasure of welcoming Derryck Reid today. Derryck has a background in physics, obtained a master's at the University of Cambridge in 1991, and then a PhD from the University of St. Andrews in 1994, working on ultrafast optical parametric oscillators. He's been then an EPSRC fellow at St. Andrews for 4 years, EPSRC research fellow, before becoming a lecturer at Heriot-Watt University in Edinburgh, and eventually advancing to professor at 2005. And he's now also head of the Institute of Photonics and Quantum Sciences there. So very much exactly right up the alley of what we're doing here as well. Derryck is also a fellow of the Optical Society of America and the Royal Society of Edinburgh, and probably best known for the invention of ultrafast pulse measurement using two-photon autocorrelation semiconductor diodes, and his demonstration of the first femtosecond frequency comb based on an OPO. Today's presentation will also be on frequency combs, in particular the development for the extremely large telescope. Very much looking forward to that. But before I hand over the stage, I still have a few technical comments and general announcements. So for number one, this seminar is being recorded. Please be aware that by participating, you implicitly agree to this. Also, as has been a tradition, you should keep your mics turned off during the presentation so that we don't get any interference here. If you have a question, type a Q into the chat channel so that we know that you want to answer, have a question, ask a question, and then we ask you to unmute and ask a question. For the most part, this will be at the end of the presentation, obviously, but if you have a really burning question, I guess we can also take that throughout. And since this is our last DLS seminar this term, as I said already, I also wanted to take a moment to thank a few people that have helped make this DLS series another success. So for one, Lothar Kuhn and his team for organizing the technical aspects of the Zoom meetings and the announcements, etc. I want to thank Lisa Spann for taking care of all the organization and communication with the speakers in the background, and in particular also to Sylvia Kuzminski, who has been co-organizing, planning the entire series and inviting the speakers in the first place. So thank you very much for doing this. And also, since I have to run off, unfortunately, for another important event halfway through, Sylvia will take over for the Q&A at the end, just so that you're not surprised if you don't see me anymore at the end, and Sylvia will then handle the discussions at the end. So that's the general announcements that I had, and I want to hand over to you, Derryck. The stage is yours.
Great, thank you, Jochen. Let me share my screen and see if we can get going. Hardest part here is always just finding the right window to share. There we go. Great. So, well, thanks, Jochen, for the kind introduction and also for the very warm, for the kind of invitation and for the very warm introduction. And yeah, it's a pleasure really to be able to come and give a talk as part of your series. So I'm going to cover, as Jochen said, I'm going to cover really the work that we've been doing at Heriot-Watt in developing new sources for frequency combs, but particularly those for astrophotonics. That's to say combs that are very wide mode spacing. Now, before I go on to that, let me just give you a little bit of calibration. So I'm in Edinburgh at the moment, which, as I checked just before the talk, is about 1,300 kilometers from Erlangen. So we're over here at Heriot-Watt University, that is in kind of the central part of Scotland. Most people in Scotland live in this little area here. And this is what Heriot-Watt University looks like. It's a fairly new university in some sense. We became a university in 1966, but we've been essentially a technical college back from maybe the mid 1800s, when the technical college was formed in order to improve, of all things, watchmaking in Edinburgh. So that's our history, and this is where I am. So in terms of, see if I can advance my slides. In terms of the talk, I'm going to base a lot of what I say about the extremely large telescope, and this is the world's largest telescope. It'll have a 39-meter diameter mirror. It's being currently constructed in the Atacama Desert in Chile, and first light is planned for 2027. So, you know, if you're an astronomer, you live with these long time scales for projects that can last decades, rather than, I guess, in photonics, we're used to these projects. Maybe a long project is maybe 5 years in photonics. Well, in astronomy, you can imagine decades, and that really is the E-ELT. It's been delayed a bit because of COVID as well. So first light will be 2027, and then the first instruments will go on, which will include basic instruments, of course, like the camera. And then in that next set of instruments, the high resolution spectrograph, high res, will be one of those. Now, as these things go, that's not yet been funded, but still there's a huge amount of work across the community internationally into planning experiments that will use high res, and also developing the instrument itself in phase A and phase B and later plans. So what the E-ELT has been built to do is really a number of things. It's going to have massive light collecting ability, far greater than any other telescope on the planet so far. And that lets it do some really fundamentally new things. So I think everyone's familiar with the idea of now detecting exoplanets by, which works something like this. And my animations are slow to start. So in terms of exoplanets, the idea is you've got a host star in our galaxy outside our solar system. It's being orbited by probably more than one planet, maybe many planets, and this combined system orbits around a common center of mass, meaning that the actual star itself is moving. You run that again. Star itself is moving relative to that kind of center of mass frame. And that means that the absorption lines that are imprinted onto the star's thermal spectrum are Doppler shifted, and they're Doppler shifted differently relative to an observer on Earth, depending on where the star is moving towards or away from us. And that in turn tells us about the gravitational pull and period of the exoplanet. So we're familiar with the idea of using large telescopes to detect exoplanets, but what the E-ELT will do is go further. It's going to enable this not just detection, but actually observation, imaging of exoplanets because of the large light collecting capacity that it has. And that extends as well to doing spectroscopy, not just of light from the star, but light from the star that has passed through the planet's atmosphere. So atmospheric spectroscopy, which is an extremely exciting part of what's going to be done, what will be possible. And so you can imagine that here's the planet with its atmosphere, and light from the star is passing through the planetary atmosphere on its way to Earth, and it's being imprinted by a number of absorption lines that correspond in the maybe visible to 2 micron region, correspond to absorptions from chemicals like oxygen, water, methane, carbon dioxide, that are the signature chemicals of life. And so that's a really exciting new development that the E-ELT will enable. So we've got exoplanets, and that's a large part of this, but there's also some more fundamental understanding of things like planetary and star formation, stellar physics, again, spectroscopically driven. And at the really most testing end, fundamental physics and cosmology, where the promise of making observations over decades with an instrument like the E-ELT is that you can not only look at the expansion of the universe, but you can look at changes in the rate of the expansion of the universe. And so tests like the Sandage-Loeb test, which look at very subtle changes in the positions of the redshift positions of spectral features from things like quasars, that allows you to understand how the rate of the universe expansion is changing. And these are very exciting and fundamental questions. So underpinning a lot of these is spectroscopy, and spectroscopy needs to be calibrated in a fully traceable sense to fundamental frequencies that are themselves atomically atomic in origin. And so that's where frequency combs come in. And one can ask, well, what kind of resolution and what kind of calibration accuracy and precision is needed for different use cases of the E-ELT? So when it comes to things like exoplanets, it's not so demanding, but you do need a broad coverage right from the visible through to the near infrared, might even call it mid-infrared at 2.4 microns. Here, the spectroscopy is really fairly standard gas type spectroscopy. So you don't need a huge precision, but something of order 50 meters per second. Now, this is not nanometers, nor is it gigahertz here. This is expressed in terms of radio velocity shift. So if you want to calibrate that in terms of wavelength, divide this radio velocity by the speed of light, and then multiply that by the wavelength or frequency of the light, and you've got an idea of the kind of precision that's needed. So this is less demanding, but some of the other applications, such as the Sandage-Loeb test, are extremely demanding. They look for precisions in the range of meters or even tens of centimeters per second. So that's of order 10 to the minus 9, 10 to the minus 10 in precision. But that's got to be traceable over probably a minimum of 2 decades. So this is where having something like a frequency comb that is atomically referenced becomes vital, because the actual spectrometer itself, it's a big diffraction grating inside a vacuum chamber. It's never going to stay fully inherently calibrated by itself over anything like that length of time. It's always got to have some independent calibration. So that's where the comb comes in. So in the extremely large telescope, the way that the spectroscopy is done is quite complex. Essentially, there's the focus of the telescope here, and then a number of fibers, multimode fibers, that route the light, which includes UV light at 380 nanometers and above, through to the infrared, routes that light down to a series of vacuum chambers that are shown here with a person for scale. And inside these vacuum chambers, each of them contains a cross-dispersed Echelle spectrograph. And at the output of that spectrograph, there will typically be a number of dichroic mirrors that separate the output into a few other spectral bands, each of those falling onto a camera covering from the UV right through to the infrared. And so that's how the spectroscopy looks. This would be what we call the high-res spectrograph in the E-ELT. And then at the center of that, there is the calibration unit. So the calibration unit, and here's for scale. This is over here. Maybe turn my laser pointer on. Over here, you can see the vacuum chambers that form the spectrograph area. The calibration unit itself is relatively small compared to those spectrographs, and the current vision for that is this, that the calibrator will be based on a white light source, an incoherent broadband light source that itself will be passed through a collection of Fabry-Perot echelons. Now, a Fabry-Perot echelon simply imprints a mode structure, spectral mode structure, onto this broadband light. And the idea is that this has got no gaps spectrally. It covers from the UV through to the mid-infrared. But although that mode structure is kind of clean. It's subject to things like dispersion in the fabric rows, and this device, because it's based on not a laser, it's probably available perpetually, throughout the whole observation time of the telescope. Whereas the laser comb, I think anyone who's worked with femtosecond lasers knows that it's really quite hard to keep them operating 24/7. But the laser comb would be used, for example, during the day to do a calibration of this calibrator unit. So really calibrating the calibrator with the frequency comb in a way that then at nighttime, this calibrator can provide a perpetual and broadband series of lines. So that's the vision for the E-ELT. And what that requires in terms of the calibrator itself, you remember that the spectrograph had certain requirements in order to supply the science cases, that maybe the most demanding was about 1 meter per second. So the calibrator's got to do even better than that, and it's got to be in the 0.1, perhaps even to the 0.01 meters per second. And that's now getting down to the 10 to minus 11, maybe 10 to minus 12 precision, which is exactly where frequency combs can operate. But you can see now the reason for needing a frequency comb. So I want to put a little bit of our work into context. There's been some good review papers in astrophotonics over the past few years. One of them, my colleague Richard McCracken and myself wrote in 2017, where we surveyed at that time all of the quite limited number of telescopes which had a frequency comb deployed on them in order to do calibration of the spectrograph. And so this chart here shows the optical coverage of the telescope, shown as a dashed box, compared to the coverage provided by the frequency comb for calibrating the spectrograph in that telescope, and that's shown in the solid colors. So you can see that really it's been quite challenging, particularly in the visible region, but also across actually most of the other infrared bands as well, to provide a comb with sufficient bandwidth that really gets anywhere close to addressing the spectral range of the telescope. And this is a dilemma for astrocombs, because an astrocomb has got to have a very broad bandwidth, but it's also got to have a wide mode spacing, sufficiently wide that you can present a series of modes from the astrocomb that the spectrograph on the telescope can resolve. So we carried out a campaign in 2016 on the South African Large Telescope, where we were able to fully cover the operating range of one of the two spectrographs there. And I'm going to tell you a bit more about that work now, and try and unpack some of the ideas of the frequency comb. So SALT is a telescope. It's a 10-meter telescope in it's about 7 hours drive north of Cape Town in South Africa. Here's the actual mirror in there, and kind of the beauty of this telescope is, unlike those run by ESO, you can actually get inside this telescope and you can see the nuts and bolts of it, and that's exactly what we did. This is a photograph of the mirror structure. It's got about 110 hexagonal mirrors that are tiled together to provide the main primary mirror. And well, that's just a gratuitous picture of some rainbows at the top of the plateau where this telescope is sited. So what do we use the frequency comb for? Well, the output of the spectrograph, and we looked at one of two spectrographs here, which is this red arm that covers, it's called the red arm, but it covers from the green to the near infrared. The output of that spectrograph is actually a camera image, 4,000 by 4,000 pixel camera image, of which the spectrum of the light is wrapped in this series of orders from this cross-dispersed shell grating that you have to then stitch together to provide the overall spectrum. And one of the neat things about the spectrograph in SALT is it has two input fibers, effectively two input slits to this spectrograph that are independent and provide, let you take two different spectra at the same time. And the idea for this is that you might take one spectrum from a source in the sky that was not aligned to your star, just to get a background, and the other spectrum you may maybe take from the star itself. And so it's about things like sky subtraction. That's the motivation for this. But what it allowed us to do was we generated a frequency comb, which are the broadband that you can see here. And zoomed in, you can see the individual comb lines. This was about a 25 gigahertz mode spacing. It allowed us to compare the output of our comb with the output from the conventional calibration source, which in this band here, in this green to red region, is a thorium argon lamp. And so while the broadbands here are the frequency comb, the ticks above that frequency comb are emission lines from this thorium argon lamp that was fed into the other fiber on the spectrograph. And you can see immediately one of the issues with this conventional source. The lines, some of them are saturated. They're very sparse. There's not very many of them at all. For example, in this order here, there's only 3 or 4 lines. Some of them are extremely faint, maybe like this one here, whereas the frequency comb gives kind of universal coverage of the spectrograph in a way that is very regular. And so if I let me see if this movie will play, and turn off my pointer. There we go. So what you'll see now is a zoomed in version, just showing us the detail of these comb lines as we pan across the spectrum. Now this is a false color image. The actual image is of course monochrome, but it's been rendered from red to green just to give a sense of the color range that you can get here. And so you can see immediately the kind of resolution that we can get with the frequency comb. So inside the telescope, this is what we have as far as the spectrograph goes. Light comes in from a fiber, a slit, and it's presented onto a curved mirror in the spectrograph that then collimates that light onto an Eschell grating. Light travels back to re-image to a confocal point here, and then it's split into 2 channels that go through cross-dispersing elements and then onto a blue camera and onto a red camera. And it's the red camera, the red channel, that we did our measurements on. So at SALT, here's the spectrograph itself. It sits inside this vacuum chamber here. So it's kind of the size of some kind of small van. And then here's the frequency comb that we built. I'm going to kind of unpack a bit about what was in that frequency comb and then explain how we're extending this for the extremely large telescope. So the comb that we used was a Ti-Sapphire frequency comb. If I go back a second, it is based on just a regular green pump Ti-Sapphire. It's a 1 gigahertz system. And this was then frequency expanded using a supercontinuum fiber, photonic crystal fiber to cover the visible range. And so with that, we then mode filtered with a Fabio Pro Echelon, mode filtered that frequency comb to create a 25 gigahertz spacing comb that covered this full range from 550 to 890 nanometers. So here you can see just a couple of those comb modes resolved on the spectrograph, and they resolve in a way that lets us just do a Gaussian fit. And from that Gaussian fit, we can get the resolution of the spectrograph at that particular point, at that particular wavelength, and in that given order. And we can go through the whole spectrograph, and we can measure the resolving power for all the orders, and we can basically characterize the spectrograph in a way that would just be impossible in any other way. And so that was what we did at SALT. We were able to improve the understanding of the resolution of the spectrograph. As a sort of side note, we were able to uncover one of an original error in the calibration of the telescope that way. And we went on to then improve the precision of the telescope by doing this fit, what's known as the wavelength solution of, in this case, one particular order, one Eschell order on the spectrograph. And here you can see that the blue symbols, those are all the different points that come from each mode of the frequency comb and give you a a position on a calibration of that particular pixel on the spectrograph, and the red symbols come from the thorium-argon lamp, the conventional calibration. And so you can see immediately that there's a massive advantage just in having so much more data to calibrate, and that reduces the error in this fairly simplistic analysis that was carried out, reduced the error by a factor of 2 in the precision. And we could also carry out an on-sky analysis. So we pointed the telescope at what's called a photometric star, one where there's a well understood absorption line, and this is the H-alpha line, which is known, or is expected to have a certain line width of between 1.33 and 1.4 angstroms. So here's the measurement, and here below it are the not perfectly resolved comb modes. I think this may have been with a 15 gigahertz mode spacing, and really calibrating the line width here of this absorption line is no more than counting these individual comb modes, and that immediately gave us a measurement that had better precision than what we could get with a thorium-argon lamp calibration. So, you get a sense here immediately of the value of having a frequency comb available on one of these telescopes. So let's maybe turn to the E-ELT calibration unit and the plans for that. So we've been working with the consortium for the E-ELT, which is run jointly between Cambridge and Florence, and so in the UK includes Heriot-Watt, Durham, Cambridge, and the UK Astronomy Technology Centre in Edinburgh. The work package for calibration is led out of Germany by Philipp Hucke at University Emden-Leer and formerly at Göttingen. And so we're contributing the comb part to that calibration work package. And we've been piloting an architecture that looks like this, where we have a source, which is a Ti-sapphire laser running at 1 gigahertz. We have routes into the visible through second harmonic generation, and into the infrared through a doubly resonant OPO. And then by using supercontinuum generation to broaden the Ti-sapphire light from 800 nanometers down to the visible and up to the near infrared, and also further supercontinuum to broaden the OPO from its central wavelength of about 1.6 microns down to 1 micron and up to 2 microns, we can cover a vast majority of the required bandwidth. And so the kind of instrumentation needed, we have to do some locking of the laser using F-to-F interferometry. We have a number of Fabric Pro ethelons to do the mode filtering. And in our approach, we're using Fourier-transform spectroscopy to measure what we're getting coming out of these filtered these filtered cavities. So let's look step by step at the components here. So here's a Ti-sapphire system. It's broadened in a photonic crystal fiber, commercial fiber from NKT. We use a little bit of this light in a home-built F-to-F interferometer based on work carried out with my group at Heriot-Watt at University and MPL in 2010. That gives us a fully locked comb, and we also lock the rep rate, and this is done just directly using radio frequency locking to a rubidium disciplined clock. So with that, we can characterize the phase noise, etc. I won't go into that in detail, but broadly speaking, this lets us have a fully locked comb. Now, the uncertainties there are still uncertainties in the comb mode positions, but when we're locking the rep rate, that's reduced to about 200 hertz. Absolute uncertainty in the optical frequency when the rep rate is locked and when the FCEO is locked. I should say that in the SALT campaign, we didn't lock the FCEO, but the kind of mirror dispersion compensated Ti-sapphire oscillators that we've been using are really quite well engineered. So the natural drift in FCEO is quite small. It's about 2 megahertz per hour, as you can see here. So we can get a supercontinuum, as shown here, and that covers from 500 to almost 1,000 or over 1,000 nanometers. We take off the longest and the shortest wavelengths for F2F locking. So we get maybe a useful band from about 550 to just a bit more than 900 nanometers that we can use for the calibration. And then we carry out mode filtering. So the way in which we've done this to date, and this is what we used in the SALT campaign, is that we use a plane Fabri-Pro Etalon. And plane works because you're basically making quite a wide mode spacing. And so there's only maybe, I don't know, a centimeter of gap between the mirrors here to get a mode spacing of between 15 and 25 gigahertz. And the mirrors that we use are dispersion matched. So that's to say that one mirror has a group delay dispersion shown like this in the green, the other has a group delay dispersion in the blue, and when you bring these together to form one cavity, you get a very flat group delay dispersion, which means that we can have both a high finesse Fabri-Pro, but also one with a very broad bandwidth. And that was really critical to our result from SALT of being able to cover the full spectral range of the spectrograph on the SALT telescope. So one of the things we've been working on at Heriot-Watt is how you identify the set of modes that you filter here. So to put this in context, in some of the other approaches taken internationally to make astrocombs, there's been an auxiliary CW laser that has been locked to a comb mode. So that's how Menlo, for example, do this on their approach in the HARP South spectrograph. We don't use an auxiliary CW laser. What we do is we lock directly to the comb, and that turns out to be a very satisfactory way of doing it. We did lock the mirror here on one of the mirrors on the Fabri-Pro Etalon, and once it's locked, it's only moving maybe only by a nanometer or something like that in order to keep it into lock, and that works well because it doesn't need an auxiliary CW laser and it doesn't need the locking of that laser to the comb. But it does mean that there is now an uncertainty about which set of comb modes we filtered. So it could be, for example, filtering every 10th mode looks like this, or it might be that filtering every 10th mode looks like this. So we've developed a Fourier-transform approach, Fourier-transform spectroscopy approach, where we have this long scan FTS, and we use that to measure the positions of the comb modes. Let me try and get my cursor back. There we go. So here's this is some work we carried out in 2017. As you'll maybe hear in a moment or two, we've developed this further more recently. But to give an idea of what you see as we scan the mirror at the arm length and the FTS, we see these interferograms, and at the same time we record with a rubidium stabilized 780 nanometer CW laser. We record a series of fringes that give us a calibration in delay for our interferograms, and from that we can simply do the Fourier transform. We can get the comb modes out, and importantly, we demonstrated in this paper that as you change the lock of the Fabri-Pro cavity, you're able to systematically with the FTS recover and identify the exact set of comb modes that you're filtering with the Fabri-Pro cavity. And so what we've moved on to do more recently in the near infrared is to show that we can now link that to our estimate or our knowledge rather of the comb mode position from radio frequency signals, from the locking signals. So I'll come on to that again in a moment or two, but I want now to talk a bit about the infrared part of the calibration light. And this is generated by taking our Ti Sapphire and pumping a doubly resonant optical parametric oscillator. So the general scheme is this: we have this X cavity doubly resonant OPO. It's made using a crystal of KTP, and then the output from this we broaden in highly nonlinear fiber. So this is some modeling of that broadening here, and here's the input pulse from the OPO. One of the really nice things about the OPO is that you can pump it with, let's say, 30 femtosecond pulses, which is about accurate for our Thai sapphire. But you can, in fact, get even shorter pulses coming out of the OPO, because the way that the gain works in the OPO is that one pump mode can basically convert into many pairs of OPO modes, and that really is a bandwidth enhancing process. So here's how things look in the lab. Here's our OPO. The green light is from some frequency mixing between the pump and the resonant OPO light. It's based on a very thin crystal of KTP that we cut at Brewster's angle, and that reduces loss in the cavity. And it has this very broad bandwidth at this thickness. So the thinner you make a nonlinear crystal, the more bandwidth you get from it. And so we get something like, I don't know, 600-700 nanometers bandwidth from this crystal, more than enough to be able to create short pulses from the OPO. So I won't go into detail, but essentially this cavity is dither locked to stabilize it and lock it permanently to the Thai sapphire comb. And the beauty of this approach is that the OPO comb inherits the stability of the Thai sapphire pump comb. So once you've characterized the Thai sapphire comb, you've basically locked and characterized the OPO comb as well. So it means that in this approach, you can basically integrate Thai sapphire and mid-infrared OPO comb modes together to form a single broadband comb. So when we take the output of the OPO and we put it into a highly nonlinear fiber, we don't need too much power actually to do that. This is 20 milliwatts up to 100 milliwatts. And you can see that 100 milliwatts from the OPO gives us a bandwidth from below 1,000 up to over 2.2 microns in wavelength. And when we put all of that together, this is what we see. So in red, we've got the Thai sapphire, original Thai sapphire spectrum. In blue, we've got the OPO spectrum. And then in green, this is the expanded PCF, photonic crystal fiber spectrum. And in black, we've got the expanded supercontinuum from the highly nonlinear fiber, which has got a power of about 50 milliwatts contained in it. So you can see here, we're able to really cover pretty much the bandwidth that we need. Getting down to the UV is still something that we're actively working on, but this gives us a lot of the bandwidth that we require. So in terms of mode filtering in the infrared, this is the approach that we've been taking. We take our OPO and we split the output. So the output comes from an intracavity mirror in the OPO, and the majority of that goes into a highly nonlinear fiber, which is what gives us the massive broadening. But we reserve a small portion, about 10% of that light, we reserve just directly from the OPO. We combine, so having split the power off here, we recombine the light using polarization multiplexing here, bring that light through and then send it into the FabriPro cavity. And here's kind of the trick. We lock the FabriPro cavity on the narrow bandwidth light that we get from the OPO, and but at the same time we send through the light from the supercontinuum that we generated, and that means that the supercontinuum gets filtered nicely by the FabriPro cavity, but it's just easier to do the locking on the unbroadened light directly from the OPO. So that's been a trick that we kind of had to learn to make this work, but now having implemented that, it works really well. And then we can take that light and we can put it into our Fourier-transform spectrometer, and we can measure the output from the OPO in that way. So here are some data that we've only published quite recently this year. Here's the output from the Fourier-transform spectrometer. Each of these is an interferogram as we scan over maybe 50 centimeters of path length. And so you can see we get maybe about a nanosecond of total scan here. Once we've kind of cropped the interferograms. And we started to do this a bit more accurately, a bit more carefully as we looked more closely at this technique. So now we window the data very carefully so that we're windowing it through the centers of interferograms. And in that way, you can avoid any systematic error when you do the Fourier transform that would otherwise give you the wrong absolute output in frequency. It's a small error, but it would be a significant error for us. Then you can do the Fourier transform. You can get the spectrum. So this is the spectrum of the supercontinuum. And the reason it's black is that there's a very dense forest of comb modes sitting inside here, which if we zoom in, we can now see the individual comb modes. And so we can put a label on each of these comb modes in terms of its mode order. And we can get that by effectively plotting a graph of mode index against frequency. And we know we've got the mode index right when the intercept of that graph hits zero frequency with a value that is between 0 and f rep. And so that's how we get the mode index here. And coming out of this, we can also get the instrument line function for the FTS. It turns out to be just a bit more than one gigahertz. And finally, this little photograph here is one of the Fabry-Perot cavities when it's locked. So there's a piezo driving a little mirror here, and here's another mirror that light travels through. So I want to just very briefly touch on the locking technique that we're now using for the OPO. As I said, when we run the OPO, we get some green light generated, and you can see that in the photograph here. This is some frequency mixing between the resonant light at 1610 and the pump light at 805. So the OPO in itself is kind of a wavelength doubler. This some frequency mixing light turns out to be really useful in locking the OPO in a way that maintains very low noise. So one of these doubly resonant OPOs, if you monitor just the output at 1600 nanometers as a function of cavity length, you see these different oscillation peaks. So as you scan the cavity, the OPO turns on, turns off, turns on, turns off. And we want to operate on this peak here that exists only for a few tens of nanometers in mirror position. Now, conventionally, one takes that peak and one has a dither locking approach where you scan over this peak. And as you scan over the peak, you electronically derive a derivative signal, and you lock at the center of that derivative signal, and that gives you the locking. But doing that means you're always shaking a mirror, and that's kind of bad for comb stability. So we've developed an approach that avoids that. We take this some frequency mixing light between the pump and the OPO. That's the green light I was telling you about. And we were able to compare the location of the peak of our infrared light from the comb, from the OPO, with where the peak of that green light occurs. And with the right spectral filtering, taking just a portion of that green light, we can arrange that we, at the peak of the OPO output, we want to lock up here, we're actually on the edge of the curve for the green light, for the power of the green light. So we do this side of fringe locking that requires no dithering, and so is a very quiet way of achieving OPO stabilization. So we've characterized that. We basically get the same output spectrum and same output power for both a dither locked OPO, DL OPO, and this side of fringe, some frequency locked OPO. So same power, same spectrum, 5 times lower power fluctuation over 1 hour, and a RIN, relative intensity noise, over 5 or 6 minutes that is again, well, factor of 7 or 8 times lower. So massively reduced noise from this system here. And again, we've characterized that a bit more carefully using power spectral density measurements, and again confirmed that this locking approach gives us very low noise. So that's covered in our 2020 paper here. So in the last few minutes, let me say a bit about some of the other work that's going on. We're particularly interested in using sources that start off at quite high repetition rates. So you'll notice that in the work we've done, we've based it around a 1 gigahertz Ti sapphire laser, and that's in contrast to some of the other work done internationally that started maybe with a 200 or 100 megahertz fiber laser maybe. And when you start at these lower comb mode spacings, you have to put a lot more effort into the modal filtering in order to suppress those original laser modes. And that becomes less necessary as you go to these wider mode-spaced lasers as a starting point for the comb. So we've looked in particular at ytterbium ceramic that operates at higher rep rates, and also at Thai sapphire that operates at higher rep rates. So starting with that Thai sapphire point, we've pumped an OPO. This is work by Richard McCracken in 2018. We've pumped a very tiny OPO with a 10 gigahertz Thai sapphire that is in fact a commercial system from Laser Quantum. And we've taken that, we configured an OPO with mirror curvatures that I think are something like 10 or 15 millimeters here. And you can see for scale, this is a 1 pence piece. And this is the output from the OPOs. This is a way of directly getting broadly spaced comb modes in the infrared. More recently, we've been looking at ways of making these higher repetition rate lasers more stable. And in something more of an engineering project, we've recently developed a self-starting 1.5 gigahertz ceramic laser, ytterbium ceramic laser, that is alignment free. So this is bonded. These mirrors are glued, precision glued onto a breadboard. And this is a £2 coin for calibration. And I'm going to show you here a little video just of this laser in operation. So what you're seeing here is the laser being turned off, that spectrum gone, turned on again. There's its output spectrum, and there's a hand for scale. So little 3D printed cover. So there's our laser, and we're going to see it being turned off just by blocking the intracavity beam, and on again. And so you get a sense that this is now a really practical engine that you could use with suitable amplification and mode broadening, mode spacing broadening, that you could use as an engine in an astrocomb. So I think I'm pretty much out of time, so let me just conclude. So I told you a bit about the SALT astrocomb campaign, and basically the main take homes from that it can improve the precision of the spectrograph, and it can characterize things like the wavelength dependent resolving power of the spectrograph. I've told you a bit about some of the work that we're doing, and this is still remains work in progress, in fact, of developing comb mode resolving Fourier-transform spectroscopy that ultimately allows us to relate directly and identify directly the set of modes that we filtered from our cavity with the comb that we know we're producing based on radio frequency data, that's FCEO and FREP. And then in terms of the E-ELT, I summarized a little bit about the calibration requirements of that as well. So this work has actually been done by a number of people, both in my research group and in collaboration with other groups. So this is a quick hall of fame of those who we've worked with, particularly those in South Africa, the group at SAAO, South African Astronomical Observatory, and also now in the E-ELT project with Philip Hookey, and some other input we've had from laser developers in Stanford and Laser Quantum and in Tokyo. So I think that is probably my last slide. I'll just leave you with a little bit of further reading some of the papers that we've generated in this project. And yeah, very happy to answer some questions. So thank you.
Thank you very much. So the floor is open for questions. You can either, yeah, Pascal, that was fast.
Okay, yes, thank you very much, Derryck. Very nice talk. I was curious, what is currently the limitation of the calibration precision of these of the spectrometers? And I'm not sure how much it's related, but how much does the pointing of the frequency comp into the spectrometer plays a role?
Yeah, so this is actually a really big headache for the community, because it turns out that it's very hard to create a laser source that really originates from exactly the same sort of virtual point as the light from the star. And yeah, I mean, the telescope, of course, is focused at a point that is you know, billions of miles away, and I think its effective focal range is still, you know, many kind of hundreds of miles or thousands of miles away from the telescope. You know, you'd have to put something at that sort of range for it to be even close to looking like a point source. So it's really difficult to get the wavefronts to match from the frequency comb or any calibrator, and from a true astronomical object. The approach that is now being considered for the E-ELT is actually a kind of hybrid approach, where it sort of says, well, this is almost inevitable that you're going to have to live with some differences, and it sort of says, well, the comb is good to give you a relative calibration, but let's put in something like an iodine cell that the light from the star travels through and imprints, let's say, a kind of iodine spectrum onto that starlight. So that gives the absolute calibration, where the comb just gives a relative calibration. And I think that's almost going to be necessary to do, because fundamentally it just is very, very difficult to otherwise arrange that, you know, even when you've got a fiber-fed spectrograph, getting the same mode quality and pointing, as you point out, it is almost impossible. And it's now becoming recognized that this is just a genuinely fundamental limit to what you might do. But I think it means that the relative calibration,
the main limitation, essentially. Or
yeah.
Okay. Yes, thank you.
Annie?
Hi, Derryck. Excellent,
Hi.
excellent. That's fascinating. So I have a question about this mid-infrared OPO that you showed. Two questions, both of them technical, about the mid-infrared. So you pump with 1.5 of titanium sapphire, and at the end in the comb you have 50 milliwatts, right? After the HNF.
Yeah, it's a bit, so numbers are a bit different. I guess we pump the OPO with probably about 900 milliwatts maybe, and the OPO, we could probably do a bit better in efficiency, but I think you tend to trade off efficiency against bandwidth sometimes. So we get, on a really good day, we get about 140 milliwatts from the OPO for about 900 milliwatts in.
Nice.
And as you saw, we've got enough peak power to get supercontinuous with, you know, tens of milliwatts very easily after that. And these highly nonlinear fibers at 1.5 microns, they're just great. It makes it very easy to get broadband light.
Yeah. So then I have also another question. So you showed this super nice mini OPO, this ceramic ytterbium KLM. So then how you align it? So the mirrors, you can rotate it from the bottom, or how do you align the cavity somehow?
Okay. So well, there were two different cavities there. One was the kind of bonded alignment-free laser. Is that the one you're talking about? Or? Yeah. Okay, so I guess there's a bit of development of jigs to hold the mirrors. So the way this is done is we have a jig arrangement. So we put one mirror down at a time. We use how many axes? I guess a 6-axis stage that the mirror is held on, and then we lower the mirror down with a small bit of glue. We orient it while the laser is mode locked. So all the mirrors start off being held in a conventional way, and then one by one we replace them with bonded mirrors. And at each stage, you know, there's kind of a day while the glue sets, and then you do the next mirror, and then you take away the last one, and you hope it still works when the glue sets. And actually, that's how it has worked. So the trick is really in having enough degrees of freedom in the kind of jigs that you use to hold the mirrors.
Oh, thank you so much.
Nick? Nick Jolie? Okay, we go to the next question. How much data is created by the telescopes you mentioned per second when they are regularly running? Question by Sven Rogachev.
Oh, well, of course, I'm not an astronomer, so hard to know. I mean, let me try and think that through. I do remember that when we were dealing with the data from the spectrograph, the files are big. So yeah, I suppose with a lot of data that comes from these telescopes is coming from instruments that were probably designed 10 to 20 years ago. I mean, it's not quite like NASA, where what you fly on the spaceship was designed 20 years ago, just so it's got, you know, robust technology. But it's maybe it's a bit like that, in that I suppose once the acquisition system is set up, these things probably change quite slowly in telescopes. It's kind of gigabytes, I imagine. It's not. I don't think it's terabytes. We're not into that sort of level of data, and this isn't particle physics. But you know, these are still big files with high resolution. Generally, you're observing in a way that you're integrating. So you know, you're not taking multiple frames. You're actually sitting staring at a star for 10 seconds, maybe longer than that. I mean, the integration times vary depending what you're looking at. So I don't suppose that really changes the sort of total amount of data.
So there is a question now. Nicolas Jolie asked, so he has having technical problems with the microphone. So he wrote me the question, any hint how to increase the generated spectrum on the UV side? So far this goes down to 500 nanometers.
Yeah, that's a really great question. So the answer is yes. It's been something I spent a lot of time on in the past sort of year. We've been working with the University of Cambridge, who have an interest in doing exactly this and getting down to about 380 nanometers, which of course is the same sort of cutoff as E-ELT. This is a different instrument on the Isaac Newton telescope. So the way in which we're going to do that now is to take a supercontinuum in the visible to near infrared and mix it with a high sapphire pulse and use some frequency mixing. And that's some frequency mixing we basically take a soliton, that's about a micron, but going down to, I think, probably a little bit less than 800 nanometers. We mix that with an 800 nanometer, you know, short, high intensity pulse. And we mix that in a waveguide, a nonlinear waveguide, and that gives us, well, we've not done the experiment yet, but that on paper, that gives us a very nice spectrum down to 380 nanometers and up to over 500. That is pretty much continuous. So when you get the design of the QPM grating correct, but yeah, this is still unproven, but it's quite a challenge because, you know, 380 to 500 nanometers doesn't feel like a lot in wavelength terms, but in frequency terms, that's actually quite a wide span to cover, and so it is quite challenging. So that's the way in which we're planning to evaluate that, and that if that goes ahead, that would be an experiment we'll probably carry out in the next 6 to 12 months.
Okay, thanks. Network?
No, you're there.
Now you can hear me. Okay.
I can see you. Hello.
We talk later anyway.
So we have another question in the chat. So from Faridullah Khan, can you get megahertz level resolution using the system? If not, is the limitation only the laser being used or anything else?
Okay, it depends which system you're asking about. If you're asking about the FTS, then the resolution is about of order of gigahertz. I mean, I think we've got down to about 700, 750 megahertz resolution from an FTS before. But that's certainly going to be close to the limit. The actual comb modes themselves, I mean, when we lock FCEO and when we lock FREP, then the absolute uncertainty in the precision of one comb mode is about 240 hertz. So, you know, that's the level of precision that we can expect in the optical once we've done the radio frequency locking. I think that maybe is the only way to answer your question, really. I mean, certainly there's a big difference in resolution between the FTS and the absolute comb precision.
So I think, but okay, I think I can squeeze a question of my own. It's a little bit more of a general, non-technical question, but I think you mentioned at the beginning. So, for example, being sensitive to expansion of the universe and to changes in it, and I was wondering what clues can that give in terms of what dark matter is and how can
okay, so I disclaimer, I'm not an astronomer, but my understanding of it is that I think it gives two things. I think it does help to explain the the sort of dark matter and dark energy balance in the universe. I think that's one thing it helps to do. I think it also gives maybe an indication directly of the fine structure constant, and perhaps I think it possibly even allows you to test if these fundamental constants like the fine structure constant are truly constant over, you know, decades. So I mean, these are really exciting big science type questions. It's going to take a generation of really patient astronomers to I guess work through the kind of data that will only become available when, you know, the femtosecond lasers that are used for calibration are totally turnkey and rock solid and, you know, able to operate kind of for the vast majority of the lifetime of the telescope. But, you know, these are clearly questions you answer over decades.
So how long? So this decades? It's like 2 decades, or?
I think it's a minimum of 1 decade. So there's a paper published on the Sandage-Loeb test, which basically says if you can measure over a decade the changes in lines that are known as the Lyman alpha forest. So if you look at the Lyman alpha emission as a UV emission that comes from quasars. So when you look at distant quasars, the redshift is very large. That UV emission that is about 120 nanometers is then shifted, I think, into the visible and maybe even into the near infrared. I guess it depends on the redshift. But you can look at all of these Lyman alpha lines, and you can then look at a model that tells you about, I think, effectively is dark matter in the universe. I think that's one of the parameters in the model. And I think the paper I looked at a while ago shows that over about a decade, you can get a useful measurement, but, you know, the longer, the better, essentially. Because I think you're just looking for a rate change in the expansion rate of the universe. So the longer you observe for, the better.
Thank you. Okay, I think there are no more questions. And so we thank you very much for the very interesting talk, and thank you everyone for participating in it. So this is the last talk of this semester series, and then we'll make a pause for a couple of months, and then we'll be starting a new series next semester. So keep tuned. Thank you very much, and bye-bye.
Thank you. Bye.